When oxygen-rich blood stalls in the narrowest channels of the human body, the surrounding tissue begins to suffocate. Standard coronary computed tomography angiography is highly effective at identifying major blockages in large arteries, but it frequently fails to resolve the capillaries, the microvascular network where ischemia often begins. This unresolved microvascular dysfunction is the underlying cause of angina in nearly 50%. Because of its anatomical position, the retina provides the only directly observable view of an active microvascular network in the human body. This is the PRISMA flowchart from a 2024 systematic review and meta-analysis. It details the rigorous methodology used to select studies, comparing the retinal metrics of coronary artery disease patients against healthy controls. By strictly filtering the literature, researchers aggregated data from over 2,400 patients, establishing a statistically robust dataset. The underlying data relies on optical coherence tomography angiography, or OCTA, an imaging modality that captures precise three-dimensional maps of retinal blood flow. Through this data, the eye becomes a strictly quantifiable map of coronary health. To accurately interpret the coronary artery disease data, we first need to map the specific vascular layers that maintain the retina's physical structure. The uppermost tier is the superficial capillary plexus, which receives its primary blood supply directly from the central retinal artery. Beneath that lies the deep capillary plexus, a network that draws additional nutritional support from the underlying choriocapillaris layer. Under healthy conditions, these distinct layers rely on intricate endothelial autoregulation, constantly adjusting vessel diameter to maintain optimal perfusion. Consequently, when systemic cardiovascular disease impairs endothelial function, perfusion strips away from these specific observable strata. The meta-analysis provides stark evidence of this exact degradation in the superficial layers. This forest plot visualizes the density of the foveal superficial vessels. The data heavily skews away from the coronary artery disease cohort, indicating a severe drop in perfusion compared to healthy controls. The pooled weighted mean difference sits at -2.19, a reduction carrying extreme statistical significance, with a p-value of less than 0.0001. The researchers noted moderate to high heterogeneity in this data, stemming from varied patient demographics and the different OCTA devices used across the individual studies. However, every single trend line points firmly in the negative direction. Irrespective of technological or population variances, the statistical record proves that coronary artery disease universally starves the superficial retinal capillary network. Moving deeper into the retina, we find the damage propagating into the deep capillary plexus and the foveal avascular zone. The foveal avascular zone is structurally unique. It entirely lacks vascular architecture of its own, relying completely on neighboring choroidal tissue for oxygenation. When the surrounding deep capillary plexus suffers a loss of perfusion, it creates a localized ischemic vacuum around the fovea, forcing the avascular zone to widen. The pooled data quantified this expansion precisely, measuring a massive 52.73 square micrometer increase in the foveal avascular area among CAD patients. This expanding void stands as a quantifiable, literal shadow cast by systemic ischemic disease. In human biology, physical tissue structure inevitably follows vascular supply. Chronic loss of perfusion in the superficial and deep plexuses dictates a measurable physical tissue loss in the eye. The CAD cohorts exhibited statistically significant decreases in the thickness of both the retinal nerve fiber layer and the subfoveal choroid. The underlying systemic mechanism driving this entire cascade is severe endothelial dysfunction, paired with a reduced production of nitric oxide. This vascular mirroring applies to other conditions as well. In patients with systemic lupus erythematosus, active retinal vasculopathy serves as an extremely accurate guide to overt autoimmune disease activity throughout the body. The retina acts as a universal physiological monitor, visibly registering the real-time degradation of both the cardiovascular and autoimmune systems. With the physiological link established, clinical focus shifts from cataloging existing damage to predicting future risk. Machine learning models can now ingest specific OCTA variables, like superficial vessel density and foveal zone expansion, to automatically generate standardized cardiovascular risk profiles, such as the syntax score. The ultimate clinical application for this technology is screening for a condition known as ischemia with no obstructive coronary arteries, or INOCA. Because INOCA is driven purely by microvascular dysfunction, it completely evades detection on standard coronary angiograms. However, its signature decay would trigger immediate red flags in an automated OCT analysis. Automated Oculomics provides physicians with a highly scalable, non-invasive screening tool capable of catching microvascular failure long before major arterial obstructions ever form. The 2024 meta-analysis does have strict scientific limitations. Most notably, the incorporated studies are cross-sectional, analyzing a single snapshot in time rather than tracking patients over years. This leaves a core question unresolved in the field of oculomics. Do these retinal vascular anomalies strictly precede coronary lesions, or do they develop synchronously alongside them? Extensive longitudinal studies are required to establish this exact physiological timeline and fully validate clinical retinal screening protocols. Regardless of whether the eye acts as an early warning system or a synchronous mirror, clinical evaluation of the retina now provides a direct, measurable window into the life expectancy of the human heart.